A planet moves through complete darkness, completely alone. That's not a story, it's a real thing. There are billions of them in our galaxy, these rogue planets, with no star at all. Just drifting in permanent night, and their existence it means we have to change what we think a planet is. It shows us the hidden, violent processes that actually build solar systems. To see how these dark worlds form, how we search for something we can't see, and what their quiet paths tell us about the galaxy itself, how a world could start in total isolation. Whether life could survive down there, in an ocean under ice that never melts, a world with no sunrise, what is that? The story of a rogue planet starts with the chaos of creation. You have a young solar system, a disk of gas and dust around a new star. Inside that disk, material is clumping together, pulling into spheres, becoming infant planets. But it's a crowded place, a violent nursery. The gravity of these growing giants tugs at everything, and in a kind of cosmic billiards, a close encounter between two large worlds can give one a slingshot of energy. It gets flung out completely, out of the star's gravitational grip. Its orbit is broken, and it's sent sailing into the deep dark between the stars. That's how many rogue planets are born. They're not failed stars, they're orphans, exiles from the systems that made them, and that distinction is important. It's crucial for understanding what they are. A rogue planet is defined as an object with the mass of a planet, but it doesn't orbit a star. Instead, it travels on its own path. It orbits the center of the galaxy directly. It's a free-floating world, bound only to the immense gravity of the Milky Way itself. To grasp that, think of our solar system as a tight family, all circling the sun. A rogue planet is a lone traveler, moving through the city of stars without a home, and then we have to separate them from another kind of dark wanderer, the brown dwarf. Both are hard to see, both drift in darkness, but they come from different origins. A brown dwarf is essentially a star that didn't quite make it. It formed from the collapse of a gas cloud like a star. But it just didn't gather enough mass, not enough to ignite sustained nuclear fusion in its core, the thing that makes a star shine. It's a faint ember cooling. A rogue planet, though, forms the way our Earth did, from the bottom up in a protoplanetary disk. It's built from the ground up. The dividing line is often mass, but more than that, it's their story. One is a failed star, the other is an exiled world, and that understanding shifts everything. It shifts our perspective. We're not looking for tiny, dark stars. We're searching for entire Earths and Jupiters that have slipped their leashes, that now wander the great abyss alone. Their existence tells us that building planets is far more dynamic, and at times far more destructive than we once thought. That violent slingshot into the void, that's just one part of it. The main idea for how they're born starts in a place of real violence, in a young solar system. You have this disk, gas and dust, everything swirling. Planets are forming inside it, pulling in more material. The biggest ones, the gas giants, they have all this gravity. And early on, when everything's crowded, their orbits aren't fixed. They can drift, they can move inward toward their star. And if two of these giants pass too close, it's a gravitational dance. It goes wrong, one of them can get flung outward like a stone from a sling. It gets so much speed it just leaves, escapes the star's pull for good. The simulations show this. It happens. It's a basic part of how planetary systems find their stable arrangement. But for the planet itself, it's a catastrophe. Think about a planet like Jupiter thrown out. That ejection is so violent it would probably tear away any moons it had. It would be left completely alone. Its atmosphere could be stripped. Its rotation could be sent into a wild spin. This idea explains a lot of the rogue giants we think are out there. They're the casualties. They're proof that building a stable solar system is turbulent. It's destructive, but then, is ejection the only path, the only way a world ends up in that kind of darkness? There's another origin story, a quieter one. Some of these dark wanderers might not have known a sun at all. They could have been born in the void, from the collapse of their own small, isolated clouds. A fragment of a nebula drifting alone, it grows cold, it contracts under its own gravity, condensing into a sphere, but it lacks the mass to become a star. To ignite that sustained nuclear fire, instead it becomes what's called a sub-brown dwarf, a world that formed exactly like a star, but on a smaller, planet-like scale. That idea reshapes the narrative. It means not every rogue planet is an exile, a victim of cosmic violence. Some are natives of the darkness, true loners. Having spent their entire existence in the deep freeze of interstellar space, this challenges what we thought we knew about what a planet is. It suggests there isn't a clean line between a star and a planet. It's more of a continuum. On one end, brilliant fusion-powered suns. In the middle, the faint, cooling embers of brown dwarfs. And on the other end, these sub-brown dwarfs. Objects that formed like stars but ended up with the mass and structure of a giant planet. They never belonged to a solar system. They were never part of one. Their home was always the great, starless expanse, and that creates a puzzle. When we detect one of these dark worlds drifting by, how do we know its history? Is it an ejected giant from a young, chaotic solar system? Or is it a primordial object, a true child of the interstellar dark? The clues are subtle. Hidden in its atmosphere, its temperature, its motion. Distinguishing between the two is one of the great detective stories in astronomy, and it leads directly to the next, even greater challenge. How do you find something that emits almost no light, something that lives in perpetual night? Finding a thing that gives off no light, it seems impossible. Like trying to find a black cat in a completely dark room. You can't see the cat, but if the cat's presence warped the room around it, if it bent the very fabric of space just by being there. That's the principle behind our most powerful tool for finding these dark wanderers, gravitational microlensing, and it comes from one of Einstein's great insights. That massive objects warp space-time, and light traveling through that warped space bends, so picture a distant star shining far away, its light streaming toward us. And then a rogue planet drifting silently passes almost perfectly between that star and our telescopes. For a moment, the planet's gravity acts like a tiny, invisible lens. It bends and focuses the starlight. The distant star seems to briefly brighten. That flash, that spike in the data, that's the planet's ghostly signature. It tells us something is there. It reveals the planet's mass through the strength and the duration of the brightening, but it tells us almost nothing else. Not its composition, not its temperature, not its atmosphere. We just know a mass of a certain size passed by. Then the light returns to normal. The event is over. The planet is gone, back into the dark. These events are incredibly rare. They need a near-perfect alignment, a background star, the rogue planet, and our line of sight. Astronomers with projects like the Optical Gravitational Lensing Experiment, OGLE, they monitor hundreds of millions of stars, night after night for years. Looking for that one telltale flicker, it's an exercise in monumental patience, and it's revealed a staggering truth, that for every star in the Milky Way, there could be dozens, even hundreds of these rogue planets. The galaxy is filled with their silent, drifting shadows. The upcoming Nancy Grace Roman Space Telescope is built to take this hunt to a new level. It will scan vast swaths of the sky, poised to catch these fleeting microlensing events with a new sensitivity. It promises to find thousands, to give us our first real census of this hidden population. But each detection is just a data point, a mass, a distance. A single note in a vast, dark symphony, so we're left with a question: if we could somehow catch one, if we could visit a world that has known only eternal night, what would we actually find? That starlight flash is just a ghost, a temporary distortion. It tells us something's there, but it doesn't show us the object itself. To really know these dark wanderers, we'd need to see their own light. And that seems impossible for a world without a sun. But in the deep cold of space, there's a faint, fading warmth. A young, massive rogue planet, one that was recently ejected or newly formed, still holds the heat of its violent birth. It glows with a dull, deep red ember in the infrared. That's our chance. That's the glimmer in the void. Our most powerful eyes for that kind of light are telescopes like the James Webb. Built to see through cosmic dust, to see the universe's heat signature, it could, in theory, pick out the faint infrared glow of a solitary giant drifting relatively close. Picture that, not a distortion of a star's light, but the direct, feeble emission from the planet's own cooling surface. A world the size of Jupiter, but isolated, its atmosphere slowly radiating away the primordial heat from its formation billions of years ago. It would appear as a single, dim pixel against the blackness, a lonely ember. The challenge is monumental. That faint infrared dot has to be distinguished from everything else that glows with heat. A distant, dusty galaxy, a faraway brown dwarf, even instrumental noise. Astronomers have to study its motion, watch it shift slightly against the fixed stars over months or years to confirm it's a solitary object within our galaxy and not something immeasurably farther away. It's a painstaking game, spot the difference, but if they succeed, that single point of light becomes a treasure trove. By analyzing the specific infrared wavelengths, scientists can start to decipher the planet's atmosphere. They might detect methane or water vapor or ammonia, clues to its composition and temperature. We move from knowing that it exists to starting to understand what it is. This direct observation paints the first, blurry portrait of a rogue world. But even this step leads to a deeper, more haunting question. What would it actually be like on the surface of a planet that has never seen a sunrise? That faint infrared glow isn't the only sign a rogue planet might give away. It could have moons. A giant planet, even after being thrown out, might have kept its moons. Or maybe it captured new ones from the chaos around its birth, and that changes things completely. A moon around a dark planet becomes a kind of beacon. Think of a moon like Europa or Enceladus, those frozen worlds around Jupiter and Saturn. They're not dead. They're warmed from the inside by the gravitational pull of their planet. That's tidal heating. The planet's gravity stretches and squeezes the moon's interior as it orbits, creating friction, creating heat. Enough heat to maintain a global ocean under the ice. So a rogue planet drifting in the cold between stars could still provide that warmth to a moon. The energy doesn't come from a star. It comes from gravity itself, a private heat source in the public dark. So you get this scenario, a planet with no sun, a moon with no sunlight, but under that ice there could be a dark, salty sea, kept liquid by the constant gravitational kneading from its planet. A pocket of warmth and chemistry in the eternal freeze. And if that ocean is there, the chemistry inside could be complex. Hydrothermal vents on the seafloor, like Earth's, could supply energy and minerals. The basic pieces for life, water, energy, chemistry, could all be there with no star at all. That turns a rogue planet from a cold relic into a potential carrier. A vessel for a hidden biosphere, traveling the galaxy in silence. But how would we know? We can't see the ocean. We can't see the moon directly, not from that far. The rogue planet is dark. Its moon would be just as dark, or maybe not. There's a glimmer. If the moon has a thin atmosphere, from geysers erupting through the ice like on Enceladus, then starlight, the general glow of the galaxy could reflect off it. Or more likely, a future telescope, something after the James Webb, might detect the faint infrared signature of the moon's own heat. not starlight, but geothermal warmth leaking from inside. It would be an achingly faint signal, a whisper of warmth against the cosmic background, but if we found it, it would be a double discovery. The moon reveals the rogue planet. And the moon's own properties hint at that hidden ocean. We'd have found not just a wanderer, but a wanderer with a secret, a dark world that might, against the odds, be a cradle. That thought pulls the search from astronomy into astrobiology. It makes us reconsider what a living world needs. Does it have to orbit a star, or can life find a way in the deep, quiet dark, sustained only by the gravitational embrace of a lonely giant? That question goes to the heart of what a world is and what it means to be alive. The idea of hidden life out there is one thing, but it's part of something much bigger. Because there are so many of these dark planets, it makes you see the galaxy differently, not just stars, but a place filled with mass we can't see, which connects to dark matter. We know it's there, we see its gravity holding galaxies together, bending light, but we've never seen what it actually is. For a long time, the main idea has been exotic particles. Things far outside normal experience, but there's another possibility, more tangible. Could a huge number of rogue planets be part of that missing mass? Not all of it, the numbers don't add up for that. Even billions of them couldn't account for all the dark matter, but they could be a piece of it, a significant piece of the ordinary matter we haven't found yet. It's like an inventory problem. We look at a galaxy, we count the stars, the gas, the dust. But if there are up to 100 rogue planets for every star like the microlensing data suggests, that's an enormous amount of mass we've missed. Mass that doesn't glow, mass that's been drifting unseen, its gravity shaping things quietly. That changes what these planets are, from curiosities to potential architects. Their combined pull could influence how stars move in clusters, shepherding them in ways we've blamed on some unknown force. They could be a kind of gravitational glue in the faint halos around galaxies. Our own Milky Way included. So when astronomers see a galaxy rotating stars at the edge, moving as fast as those near the center, that classic dark matter signal, some part of that unseen anchor could be these frozen worlds. They become part of the hidden skeleton. The narrative shifts completely. We're not just talking about lonely worlds or possible life anymore. We're talking about a fundamental part of galactic structure itself. A dark planetary population that's been here all along, woven into the fabric of everything, its gravity quietly guiding the dance of the stars. And if that's true, then searching for these worlds isn't just about finding planets. It's about mapping the invisible architecture of our home. Most of the ones we can find are giants, Jupiter-sized worlds. They're the easiest to spot through microlensing or that faint infrared signature. Their scale is hard to grasp, a planet 10 times the mass of Jupiter, a sphere of hydrogen and helium so large it could hold 1,000 Earths, but it's not orbiting anything. It's drifting. Its atmosphere, that churning sea of gas normally energized by a star, is frozen in a kind of suspension. The great storms on Jupiter, the bands and vortices, they're driven by the sun's heat and the planet's own internal furnace. For a rogue giant, that solar energy is gone. Only the planet's own primordial warmth is left, a deep ember from its violent formation. That heat still leaks from the core, rising through layers of metallic hydrogen, maybe driving some sluggish global circulation. But over billions of years, that heat fades, the planet cools, and as it cools, its atmosphere does something alien. Without the churning force of a star, the planet-wide weather might gradually settle. The upper layers, growing colder, could let exotic compounds condense. Not just water ice, but clouds of ammonia, methane, nitrogen. They might form layers like a cosmic onion. Hazes of hydrocarbon snow falling into deeper, warmer levels where they evaporate again. It could be a world of slow, perpetual distillation, where the sky itself gradually freezes into strange ices. And then the magnetic field. A planet like Jupiter has a monstrous magnetic field generated by the churning of metallic hydrogen deep inside. For a rogue giant, that dynamo might still be active, powered by its lingering internal heat and its slow rotation. So this dark, frozen world could be a silent, planet-sized magnet, sailing through the galaxy, its own invisible magnetic bubble pushing against the weak interstellar fields. Charged particles from space, cosmic rays, would spiral along its magnetic lines, maybe creating faint, permanent auroras at its poles, a shimmering, invisible light show in a sky with no star. That's the portrait of the most common rogue, not a rocky world but a fading gas giant, a relic of a solar system's early chaos, now becoming a frozen, layered, magnetized ghost. Carrying the last whispers of its birth heat into an endless night, a gas giant is one kind of wanderer, but there's another kind, a world like ours, a rocky planet, an Earth thrown out into the dark. That idea is more haunting. Imagine a sphere of rock and iron about the size of our home. It forms in the warm part of a star system where water can be liquid. It might even have oceans early on, but then the gravitational chaos starts, a close pass with a giant planet, a violent nudge, and this young world is ejected. It's flung from the light and warmth of its sun into the deep freeze of interstellar space. The change would be fast and catastrophic. Without a star, the surface temperature plummets. Not to zero, not to -100, but to near absolute zero. -270 degrees Celsius, the cold of the cosmic background itself. Any atmosphere it had, any thick blanket of nitrogen or carbon dioxide, wouldn't just thin out, it would freeze solid, it would collapse, falling as snow onto the surface. The oceans, if they existed, would freeze completely, not just a layer of ice on top, but a global glaciation all the way down to the seabed. The whole planet becomes a single, solid ice ball, kilometers thick over a rocky core. It becomes a geological tomb. On Earth, our planet's heart is kept hot by radioactive decay in the core, and that heat drives everything. It moves continents, it fuels volcanoes, it cycles carbon through the mantle. But a lone, Earth-sized world is too small. Its internal heat would leak away into the immense cold of space much more quickly. Within a billion years or so, that geological engine would sputter and stop. The core would solidify, the mantle would freeze into place, all tectonic activity, all volcanism would cease forever. The planet becomes inert, a silent, frozen sphere of rock and ice adrift in an eternal night. It's the ultimate stillness, a world that is, in the most profound sense, dead. Yet in that death, in that absolute preservation, there's an incredible value. This frozen tomb becomes a perfect time capsule. Think of our own Earth. Our surface is constantly recycled. Erosion, plate tectonics, volcanism, they churn the rock and erase the past. The earliest chapters of our planet's story are almost completely lost. But on a rogue terrestrial world, that process stops the moment it's ejected. Its surface is flash frozen, then locked in stasis for billions of years. The composition of its original atmosphere is preserved as layers of exotic ice. The chemistry of its primordial oceans is trapped in the deep glacial ice. The record of the impacts it suffered in its youth, the craters from the early solar system, would remain perfectly crisp, untouched by wind or rain. It's a museum exhibit from the dawn of planetary formation, a pristine record of what a rocky world was like before its star system settled down. For a future civilization that could reach it, such a world would be an archaeologist's dream. A single, undisturbed page from the earliest chapter of galactic history, waiting in the dark to be read. That frozen tomb isn't the only outcome for a rocky world. There's another path. It changes a dark wanderer from a geological relic into something else entirely. You can look at our own solar system, Europa orbiting Jupiter. It's a frozen ball of ice, but beneath that ice, scientists are confident there's a global ocean, a salty ocean, and the heat that keeps it liquid doesn't come from the sun. It comes from within. Jupiter's gravity stretches and squeezes Europa's core. That friction creates warmth. That's tidal heating. Now take that principle. Apply it to a rogue planet, not a gas giant, a rocky world, maybe 1 or 2 times the size of Earth, a super-sized Europa, but with no Jupiter to tug on it. So where does its heat come from? The answer is in the rocks, radioactive elements, uranium, thorium, potassium. They're woven into the fabric of a rocky planet. These elements decay over billions of years. They release heat. On Earth, that internal furnace drives our geology. On a rogue planet, sealed in the deep freeze of space, that radioactive decay becomes a private sun. It gives just enough warmth, enough to keep the whole world from freezing solid. The surface, exposed to the vacuum, would still be an icy wasteland. Nearly absolute zero, but beneath that, a thick shell of ice, maybe tens of kilometers thick. It acts as a perfect insulator. It traps the planet's own geothermal heat. And below that ice shell, the temperature rises. It rises enough for a vast global ocean to exist, a dark, sunless sea, wrapped in ice, floating in the interstellar void. This isn't a small lake. This is a body of water that could hold more liquid than all of Earth's oceans combined, a sealed aquatic environment, completely isolated from the universe. Potentially stable for billions of years, the chemistry inside could be rich, hydrothermal vents on the ocean floor, fueled by the planet's internal heat. They'd spew minerals and energy into the water, the basic ingredients for organic chemistry: water, heat, minerals, time. They're all there. In that eternal darkness, far from any star, complex molecules could form. They could interact. This shifts the whole narrative. A rogue planet is no longer just a frozen tomb or a silent magnet. It becomes a potential biological ark. A self-contained world with its own internal energy source, sailing the galaxy. It raises a question, a reflective one. Could the spark of life ignite in such a place? Not on the surface, in the sunlight, but in the quiet, pressurized dark of a subsurface abyss. If life can emerge around Earth's deep-sea vents, using chemical energy instead of sunlight, then why not here? In this isolated, sunless aquarium, the rules are different, the timescales are immense, the environment is stable beyond anything we know. It's a thought that redefines loneliness. Not as an empty void, but as a vessel, carrying its own hidden, watery world within, a nomad with a secret ocean, holding possibilities we are only beginning to understand. A world without a sun, its atmosphere follows different laws. On Earth, weather is solar-powered. Sunlight heats the ground, air rises, winds start, clouds form. It's a dynamic system, but take the sun away, you remove that primary driver. What's left is a slow, cold physics, governed only by the planet's own fading internal warmth and the deep chill of space. For a rogue gas giant, this creates conditions that are hard to picture. As it cools over billions of years, its huge atmosphere, once a churning soup of hydrogen and helium, begins to stratify. The deepest layers, warmed from the core, might stay a turbulent sea of metallic hydrogen, but higher up, temperatures plummet. In these frigid zones, gases that stay airborne on a warm Jupiter start to condense. Not just water vapor, but exotic compounds. Methane could form clouds, fall as a slow, viscous rain. On a sufficiently cold giant, even helium might liquefy and precipitate. A drizzle of liquid helium falling through a haze of frozen nitrogen, descending into warmer depths only to evaporate and rise again. It's a global distillation cycle, achingly slow. The sky gradually separates into its chemical components. The weather isn't about storms, but about sedimentation, a gradual settling of the atmosphere into layers. Like a cosmic cocktail left undisturbed for eons, For a rocky rogue with some internal heat, the atmospheric story is stranger. If it retained or outgassed any atmosphere after ejection, it wouldn't be an air we could breathe. With no solar wind or ultraviolet light to blast molecules away, the gases that remain would be the heaviest, the most reluctant to escape, an incredibly thin, tenuous shroud clinging to the frozen surface. Not nitrogen or oxygen, but dense, noble gases, xenon or radon seeping up from radioactive rocks below. This atmosphere would be utterly stagnant near the surface, no wind to speak of. But higher up, warmed slightly by faint geothermal heat radiating from the planet, a feeble convection might begin. The heavy, cold gas at the surface could slowly sink, while slightly warmer gas from above descends to take its place. A whisper of circulation, a ghost of weather happening over geological timescales. The entire system is a study in extreme patience. A single convective cycle might take 10,000 years. No seasons, no day-night cycle, no storms, just a perpetual freezing twilight. A sky so thin and clear the galaxy's stars would shine down with impossible, unwinking brilliance onto a frozen, silent landscape. This is the alien climatology of eternal night, where meteorology becomes a branch of cryogenics, and the sky itself is a slow-motion experiment in chemistry and decay. They don't all drift the same way. Each one has its own speed, a velocity that's part of it from the start. That speed tells you its story. Take a planet kicked out of a young system. It doesn't just wander off, it gets flung. It keeps all the orbital speed it had and then gets an extra kick. So it's moving fast, incredibly fast, hundreds of thousands of kilometers an hour. This isn't drifting, it's an escape, and its path isn't curved. It's what they call hyperbolic, an open arc. It won't come back. It's a one-way trip out into the dark between the spiral arms, maybe even out of the galaxy, given enough time. That motion is a signature. It's the mark of a catastrophe, but then you have the ones born in the dark, like a sub-brown dwarf forming from its own lonely cloud. That object never orbited a star. It formed from a cloud that was already drifting slowly, so its inherited motion is calm, stately, maybe just tens of thousands of kilometers an hour. A gentle drift, its path isn't a hyperbola. It's a quiet orbit around the galaxy like the stars. That speed is a clue to a different origin, one of isolation, not expulsion. For an astronomer, this difference in motion is evidence. You track a faint dot over years. You measure its tiny shift, its proper motion, and its radial velocity. You reconstruct its path. Does it trace back to a star-forming region, to the scene of the crime, or does it just move with the general flow? The speed becomes a biography. A fast one whispers of chaos, of a young system's violence. A slow one suggests something solitary, something primordial. This testimony, written in velocity, lets you start to sort them. The orphans from the hermits, and it makes you wonder, if they're moving that fast, where are they all going? That speed, that motion, it's just one piece of data. But the numbers we're starting to see are staggering. From the microlensing events we've caught and the models built from them, astronomers are putting together a new picture. A galactic census, and it's pointing to something. It suggests the Milky Way isn't mainly a place of stars with planets. It's a place filled with planets that have no stars. Recent studies estimate there could be billions of these rogue worlds in our galaxy. Some models even put the number in the trillions. For every star you see, there could be dozens, even hundreds of these dark, drifting worlds. They don't just outnumber planets in solar systems, they could outnumber the stars themselves. Think about that scale, the spiral arms of the Milky Way, that disk of light. Now imagine the spaces between those points of light filled with countless invisible spheres, a hidden swarm, a vast population of dark objects, each one a world silently moving on its own path. They're the galaxy's silent majority. This isn't a handful of oddities. This is a fundamental part of galactic structure. Their combined mass is significant. Their gravitational influence, subtle but pervasive, is woven into everything. What does this abundance tell us? It forces a shift in how we think planets form. If ejection were a rare accident, we wouldn't see these numbers, but billions upon billions suggest something else. That violent gravitational scattering we see in simulations, it isn't a bug. It's a feature, a common, even expected outcome. When a young star forms with a disk, building planets is messy and chaotic. The formation of giant planets almost guarantees that some smaller siblings, or even other giants, get gravitationally bullied, nudged, or thrown out. This isn't planetary formation failing. This is it working as designed. The efficiency isn't in building a tidy, stable system like ours. The efficiency is in building planets, period. And for every Earth or Jupiter that finds a stable orbit, another might be cast out into the dark. Our own solar system, with its orderly planets, might be the exception. The quiet suburb in a galaxy of chaotic construction sites. This immense dark population implies ejection is a standard part of the production line. It means for every story of a world finding its place in the light, there's a parallel story of a world beginning an endless journey in the dark. This changes the narrative from loss to proliferation. The galaxy isn't just making planets to keep, it's making planets to set free. All that talk about billions of dark wanderers out in the galaxy. It makes you wonder if one could be here, right now, in our own solar system. And that idea, it's not just a story, it's a real scientific possibility. It comes from something strange happening way out in the frozen edges of our system. Beyond Neptune, in the Kuiper belt, there are thousands of small, icy objects out there orbiting. But their orbits aren't random. Astronomers see a pattern. The most distant ones, their paths are clustered, aligned, as if something massive is tugging on them. Something we can't see. The main explanation for that gravitational nudge is a hypothetical planet. They call it Planet 9, a world several times Earth's mass. On a huge, elliptical orbit that takes thousands of years to go around the Sun. But here's the thing, Planet 9, if it's real, it's not a rogue planet. It belongs to our solar system. It's bound to the Sun. It's a native, just a very distant one. It always comes back, but there's another, more radical idea. Maybe the thing shepherding those orbits isn't a native at all. Maybe it's an interstellar visitor that got caught. A true rogue planet drifting through the galaxy, passed close enough to our Sun that our gravity captured it. Snared it into a permanent but wild orbit. That would be an interloper, a cosmic drifter that found a home here. The evidence in the Kuiper belt would look the same either way. The gravitational anomalies, but the stories behind them would be completely different. One is a long-lost sibling, formed with our solar system and thrown to the edge long ago. The other is an adopted orphan, a solitary wanderer from another star entirely now tied to ours. The capture idea is less likely, but it's not impossible. In those dense stellar nurseries where stars are born, systems pass close to each other. A planet could be stripped from one star and gently snagged by another. A cosmic exchange. If that happened in our solar system's violent youth, a captured rogue could have been circling in the dark ever since. Its influence only now being felt through the delicate dance of those distant ice chunks. That connection ties the galactic scale right to our doorstep. The search for Planet 9 isn't just about finding another world. It's a test. Are those strange orbits the signature of a planet from our own chaotic past? Or are they the mark of an immigrant? A captured rogue would be a frozen time capsule from another star. A chance to study, up close, the makeup and history of a world that formed around a different sun. Its presence would rewrite the story of our solar system's formation. It would introduce an element of interstellar exchange we're only starting to understand. The hunt goes on. telescopes scanning the frozen depths for that faint, moving dot. Whether it's a native giant or a captured wanderer, finding it would do more than fill a blank on a chart. It would place our solar system into the broader story of the galaxy. It would show the boundary between here and out there is more porous than we knew. That the dark, drifting worlds of the cosmos might not be as distant as they seem. A solar system has a quiet order. It's delicate. Planets, asteroids, even that distant cloud of comets, they're all held in a gravitational balance. That balance lasts billions of years, but if you introduce a new mass, something dark and silent, the balance trembles. Think of a rogue planet drifting on its path through the galaxy. It passes through the outer reaches of a system like ours. It doesn't need to collide. It doesn't even need to come very close. Its gravity alone is enough. Like a stone thrown into a still pond, the ripples it creates are profound. They last a long time. Now, the most distant part of our solar system is the Oort cloud. A vast spherical shell of icy objects far beyond Pluto. These are the raw ingredients of comets. They're held in a loose gravitational embrace by the Sun. They orbit slowly, a fragile equilibrium. A passing rogue planet, even one several times the mass of Earth, would pull on these icy bodies. It wouldn't capture them. It would nudge them, perturb their orbits, give some of them just enough of a push to send them falling inward, toward the heart of the solar system. What was a stable, frozen reservoir becomes a source of new comets, a celestial shower, triggered by a dark and silent visitor. This isn't fantasy. It's a plausible astronomical mechanism. Our own solar system's history is written in rock layers in the fossil record. It shows periods of increased bombardment, times when more comets and asteroids seem to have struck the inner planets. One leading hypothesis is that something disturbed the Oort cloud. The gravitational influence of a passing star is one possibility. But a rogue planet, dark and undetectable to us, could have the same effect. It could be the unseen architect of a comet shower, a shower that rains down over millions of years. The visitor would be long gone by then, continuing its journey into the void, leaving behind a chaotic legacy, new streaks of light in a planet's sky, and potentially new craters on its surface. This idea reframes chapters in Earth's deep past. Periods of significant change in the fossil record, where many forms of life faded away, have been linked by researchers to evidence of major impacts. A single, catastrophic asteroid strike gets a lot of focus, but a sustained period of increased comet activity could apply environmental pressure over a longer timescale, challenging ecosystems in different ways. The cause of that activity might not be a visible event within our system. It could be a silent, dark transit from outside it. So our planet's story may include not just its own evolution, but also the subtle gravitational scars left by distant, wandering worlds that pass through our neighborhood in the night. It suggests the history of life on one world can be quietly intertwined with the lonely journey of another. A connection made across light years, written not in light but in gravity and stone. The journey doesn't always end in the void. A rogue planet's path is solitary, but the galaxy is crowded. There's another fate, a cosmic second chance, adoption. You have a dark wanderer drifting for 1 billion years. Its trajectory carries it by chance near a passing star system, not a collision, a close gravitational encounter. For capture to happen, the conditions have to be perfect. The rogue has to lose just enough speed. It needs to shed its excess kinetic energy, the energy that keeps it free. That often requires a third body, a gravitational brake. The rogue might pass close to a giant planet in that foreign system. That planet's gravity can siphon off the speed, nudging the visitor from a hyperbolic escape path into a bound orbit. An elliptical orbit around the new star. It's a delicate gravitational dance, a cosmic transaction of energy. The most likely places for this are the busiest neighborhoods. Dense star clusters, or intriguingly, binary star systems. In a binary system with two stars orbiting each other, the gravitational interplay is complex. It creates more opportunities for a passing object to be captured. It's a chaotic environment. Orbits are less stable there. The chances for this kind of celestial adoption are higher. A captured rogue would bear the scars of its origin forever. It wouldn't enter its new home on a neat, circular path. Its orbit would be wildly eccentric. Extremely elongated, a testament to its traumatic past. It would spend most of its time in the frozen outer reaches of its adopted system, swinging in for a brief, blistering close pass to the star. Then being flung back out into the dark. This very signature, a massive planet on a bizarre, tilted, extremely stretched orbit, is something astronomers are starting to see. In other star systems, planets that, according to traditional formation models, have no business being where they are, their strange paths could be the clearest evidence we have. Evidence of interstellar capture events. They are not native-born to their sun. They are immigrants. Their history is written in the shape of their lonely, looping journeys. A captured rogue planet becomes a permanent monument to chaos, a world with two histories, one born in light or darkness around an unknown star, and a second life beginning with a gravitational embrace it never expected. A planet drifting alone isn't silent. It has a magnetic voice, a whisper. Every planet with a molten core can make a magnetic field. Earth does. It's a bubble that pushes away the sun's particles. Jupiter's field is huge, and for a rogue planet, a gas giant, that field doesn't just vanish, it stays, a planet-sized magnet sailing through the galaxy. But its environment is completely different. There's no constant wind from a star, no stream of particles to crash against that magnetic bubble, no bright bow shock. Instead, the field pushes against something much more subtle. The interstellar medium, space, isn't empty. It's a thin soup, gas, dust, and it's threaded by the galaxy's own faint magnetic fields. So as the planet moves, its magnetic field plows through this fabric. The interaction is slow, complex. The galaxy's magnetic lines drape around the planet's field. They stretch, they snap. Charged particles, cosmic rays moving near light speed, get caught in this magnetic maze. They spiral along the field lines. They accelerate, and this process, this gentle friction between a wandering magnet and the galaxy, could make something. A faint, ultra-low-frequency radio emission. A hum, a magnetic song on wavelengths kilometers long. It would be a lonely signal, incredibly weak, drowned out by the radio noise from stars, from galaxies, from us. Our telescopes can't hear it now. It's a whisper in a hurricane, but the next generation of observatories, maybe on the far side of the moon or in deep space, they might be sensitive enough. They could tune to the deepest, quietest bands and listen. If they could isolate that drifting signature, it would be a revelation. We wouldn't be seeing a distortion of light. We'd be hearing the planet directly, its magnetic field translated into sound, a fingerprint of its internal dynamo, its rotation. Each planet's song would be unique. Shaped by the strength of its field, its rotation speed, the density of the medium it's moving through. A fast-moving ejected giant might sing a different, more turbulent note than a slow drifting one. This magnetic whisper is a direct line into the planet's heart. By decoding that song, we could learn about the churning of metallic hydrogen deep in its core. Long after its star is gone, we could gauge its rotation period, a day that lasts for hours in a night that lasts forever. We could even map, in a crude way, the magnetic geography of the galaxy it travels through. By how the medium changes the signal, it turns the rogue planet from a silent, dark statue into a broadcaster, a chronicler of its own journey, singing a quiet ballad of isolation into the dark. A ballad we are only now learning how to hear. The magnetic whisper is one story, but there's another, chemistry. You take the basic ingredients of life and put them in a kitchen of permanent night. Sunlight seems essential, but maybe it isn't on a rogue world deep in a subsurface ocean. The energy isn't from a star, it's geology, hydrothermal vents on the ocean floor. Fueled by the planet's own radioactive warmth, they spew minerals and superheated water into the cold, dark sea. That creates a gradient, a difference in temperature and chemistry. And that gradient is usable energy. It drives complex reactions. On Earth, we call these black smokers, towering chimneys of mineral deposits, where scalding, chemical-rich water meets the icy ocean. And around them, in total darkness, entire ecosystems thrive. They don't use the sun. Their base is chemosynthesis, microbes that harness chemical energy from the vent fluids to build organic molecules. They're the foundation. So a stable, sunless environment with a consistent energy source can sustain life. But could it start there? Could the first steps from non-living chemistry to a living cell happen in that place? Experiments and theories suggest it could. The classic idea is a prebiotic soup, a warm, sunlit pond, but the deep ocean floor might be better, high pressure. Shielded from surface chaos, the minerals in vent structures can act as catalysts, helping simple molecules link together, water, carbon dioxide, ammonia. Forming more complex organic chains, the porous rock provides microscopic chambers, concentrating these chemicals, letting them interact over immense timescales. On a rogue planet, this kitchen is undisturbed. No day-night cycle, no seasons, no surface storms, just constant, gentle warmth from below, a steady supply of chemistry from the planet's interior. The experiment could run for 1 billion years without interruption, and the raw ingredients, they come from the stars. Interstellar clouds aren't empty. They're factories of organic chemistry. Astronomers with radio telescopes have detected a stunning array of complex molecules drifting there, alcohols, sugars, even amino acids, the building blocks of proteins. They form on dust grains in the cold vacuum of space, activated by starlight and cosmic rays. When a star and planets form, they inherit this chemical legacy. So a rogue planet carries these molecular seeds within its rock and ice. The concept is profound. The building blocks of life aren't rare or special to Earth. They're universal, written into the chemistry of the galaxy. A rogue planet offers a stable, patient kitchen. A dark, pressurized ocean without ultraviolet radiation to break molecules apart, without asteroid impacts to sterilize the surface. The delicate work of chemical evolution proceeds in quiet darkness. Life might not be an accident of light. It might be a potential inherent in the cold, dark chemistry of the cosmos, waiting for the right stable, warm, wet place to express itself. Even if that place is a sealed ocean adrift between the stars, that undisturbed chemistry opens up a real possibility. These dark wanderers could be the universe's ultimate time capsules. You think about Earth's own history. Our surface is dynamic, constantly erasing its own past. Wind and rain wear down mountains. Plate tectonics takes entire ocean floors and pulls them down, melts the rock, recycles it back into the mantle. Volcanic eruptions lay down new landscapes. That geological churn is why we have so few rocks from the planet's first billion years. The early chapters are just gone. Now take a rogue terrestrial world, ejected early in its star system's life. Its surface flash freezes. All geological activity stops permanently. Any atmosphere collapses into layers of exotic ice. The planet enters a state of profound stasis. Shielded from a star's radiation, from solar wind, its surface becomes a museum exhibit, a perfectly preserved snapshot from the dawn of planetary formation. The craters from the last great bombardment, the chemical composition of its primordial crust, even the isotopic ratios in its rocks, all of it remains exactly as it was over 4 billion years ago. For a planetary scientist, that world would be an archaeological treasure beyond price. It would hold answers to questions we can only guess at from the fragmented, recycled geology here. What was the exact mix of materials in that part of the galaxy? How quickly did planetesimals accrete? What were the conditions in the protoplanetary disk during those first critical millions of years? A rogue planet is a sealed vault holding that data, but the value multiplies if such a world were ever captured by our own solar system. Imagine a future where we could visit a captured rogue, an immigrant from another star. Landing on its frozen surface would be like a sample return mission from an alien solar system without having to cross the interstellar void. We could directly compare its pristine material to our own. Is the ratio of certain isotopes different? Does it contain minerals or compounds we've never seen? Each scoop of ice, each fragment of ancient rock would be a page from another star's history book. It would tell us how typical or how unique our own solar system's formation really was. So these rogue planets become more than curiosities, more than potential cradles. They are custodians of cosmic memory, silent archivists holding the original records of creation, waiting in the dark for a reader. That cosmic memory, though, it becomes a problem for anyone trying to travel later. Because the galaxy has this silent population, these dark wanderers, and that changes what empty space means. For a ship going between stars, the void isn't empty. It's an ocean full of masses you can't see, just drifting. At sub-light speeds, hitting even a small icy body would be catastrophic, but the danger isn't just the impact. The main hazard is their gravity. A rogue planet's gravitational field stretches out far beyond the body itself. It warps the space around it. For a ship moving at a big fraction of light speed, approaching that gravity, well, it would be like hitting an invisible wall. The ship's path would get bent violently. Tidal forces could tear it apart long before you'd see it on radar or visually. So it reframes the map. The spiral arms aren't just lanes of stars. They're a terrain littered with gravitational potholes. These dark planetary objects become like submerged reefs in a shipping lane. To navigate that safely, a generation ship would need a detection system we don't have. Radar and telescopes are useless against something cold and dark light years away. The ship would need to see gravity itself. Maybe it uses a network of probes sent years ahead, mapping the gravitational landscape by sending back data on how their own paths get minutely perturbed. Or it could use an array to detect the faint distortion of background starlight, a constant microlensing survey of the path ahead. Another idea is monitoring the interstellar medium itself. A massive object's gravity would subtly gather the thin gas and dust, create a detectable bow wave in space that the ship could sense. That turns interstellar travel from plotting a course between 2 points of light into an exercise in dynamic gravitational cartography. The ship's computer isn't just a navigator. It's a geologist constantly analyzing the unseen topography of the galaxy, recalculating the route to avoid the dark masses drifting out there, so the rogue planets aren't just subjects for study. They become environmental constants, factors of physics and geography. Any civilization wanting to cross the stars has to account for them. They make sure the galaxy stays a place of mystery and risk. Its darkest corners hold these quiet, gravitational guardians. They demand respect. A rogue planet is a solitary giant, but the darkness can hold more than that. You can have a binary pair, two planetary objects locked in a gravitational embrace, drifting together through the void, a system within a system, a tiny, isolated clock ticking in the emptiness. That's a free-floating binary, and it's not just possible, it's likely. How does a pair like that form? One way is a shared ejection. In the chaotic early days of a solar system, two large protoplanets might form close together. Their gravity binds them in a tight dance. Then, when a gravitational instability hits, when a giant planet comes barreling through, the pair gets flung out together. They're ejected as a single unit, a double exile. Their shared momentum carries them out of the star's grasp, and they take their dance with them into the dark. Another possibility is capture. Two solitary rogue planets drifting on similar paths pass close enough for their gravity to snare each other. In the vastness, that's a rare event. But given billions of years and countless wanderers, rare events become inevitable. They form a new partnership, orbiting a common center of mass between them. Their dance in total darkness is complex. Without a star's gravity to dictate the rules, their mutual orbit defines their universe. The tides between them become a powerful force. As they circle each other, their gravitational pulls stretch and squeeze their interiors. This constant flexing generates friction, and friction creates heat. This tidal heating could be significant, especially if their orbits are eccentric, more oval than circular. For a pair of rocky worlds, this internal warmth could be the difference between a frozen tomb and a subsurface ocean. One world's gravity could keep the other's interior churning, maintaining geological activity long after a solitary world would have gone cold. It's a partnership of survival. They provide each other with a private energy source, a reason to stay warm in the eternal freeze. This adds a new layer to the rogue planet family. We move from solitary wanderers to couples. From orphans to families, a binary rogue system is a self-contained gravitational experiment. Its dynamics tell a story about its formation. Was it born together, or did it find companionship later? The stability of its orbit, the distance between the pair, the potential for exchanged material if they are close enough, all of it paints a richer picture of interactions in the dark. It suggests that even in the most isolated reaches, gravity finds a way to create relationship and complexity. A tiny, silent duet performing for an audience of none on a stage that spans the galaxy. Neptune is a mystery even in its own neighborhood. It's not a gas giant like Jupiter. It's an ice giant, a different kind of world. Its interior is a deep ocean of water, methane, and ammonia ices under pressure, wrapped in a thick atmosphere. It formed far out where the disk was cold and rich in those icy compounds, and that location creates a paradox for rogue planets. If ejection comes from chaos in the inner system, how does a world that formed in the quiet, distant outskirts get thrown out? Its presence in the rogue population is a clue to a deeper, more systemic violence. The traditional view had a certain order. Rocky worlds form close to the star. Gas giants form farther out, ice giants form farther still. Their orbits are presumed stable, settled from the start. But if we're finding rogue ice giants worlds with the composition of Neptune but sailing alone, that story is incomplete. It means the instability isn't confined to the inner system. It can ripple outward, engulfing the entire planetary family. One explanation is planetary migration. We see evidence that giant planets can move inward after they form. As a gas giant like Jupiter migrates, its gravity acts like a plow. It scatters everything in its path. Smaller planets, asteroids, and crucially, it can perturb the orbits of the ice giants farther out. It might fling one outward entirely, a slingshot into interstellar space. Or it could trigger a chain reaction. A nudge from the migrating giant sends an ice giant into a chaotic dance with its siblings. In that gravitational exchange, one loses. It gets ejected as a casualty. This isn't a quiet process. It's a system-wide rearrangement. The ejection of an ice giant becomes a signature event. It marks the moment a young solar system reordered its fundamental architecture. So when astronomers estimate the ratio of rogue ice giants to rogue gas giants, they're reading a statistical report, a report from cosmic adolescence. A high number of wandering Neptunes would tell us that violent migration is common, perhaps even routine. our own solar system might have experienced this. Some models suggest we once had a fifth giant planet, an ice giant ejected in the early chaos. That lost world could be out there now, a dark, frozen twin to Neptune drifting in the perpetual night. Its absence here is a silent witness, a witness to the turmoil of our youth. Finding and counting these exiled ice giants, then, is more than cataloging oddities. Each one is a fossilized record, a record of a solar system's most turbulent growing pains. They tell us the quiet orbits we see today are the survivors. Survivors of a much more dramatic and destructive past. The darkness between the stars holds not just orphans but refugees. Refugees from wars of gravity that reshaped entire families of worlds. That internal warmth is a clock, it's ticking down. Every rogue planet carries the fading heat of its creation. That heat tells its life story, the journey from a molten birth to a final, uniform chill. It's a slow transformation. It spans billions of years. It starts with the energy of formation, whether it coalesced from a disk or collapsed from a cloud. That process releases a huge amount of gravitational energy. It turns into heat. For a young giant, the core is a furnace. For a rocky world, the interior is a churning sea of magma. That's the planet's inheritance, its only source of energy once it leaves the light of a star. The cooling curve isn't a straight line. At first, the heat loss is rapid. The planet radiates its intense birth heat into space. The outer layers cool and solidify first. For a gas giant, the atmosphere begins to stratify. Exotic compounds condense out. For a terrestrial world with water, this is a critical window. If it has enough mass and radioactive elements, this early phase might sustain a subsurface ocean. For a long time, the internal warmth keeps the high-pressure ice at the ocean floor from thickening too quickly. It maintains a liquid layer. This could be a temperate phase, lasting perhaps 1 billion years or more, a hidden, aquatic golden age in the dark. But the heat always loses. The core's radioactive fuel decays. The primordial warmth slowly bleeds away into space. The planet's insulating layers, a thick ice shell or a deep atmosphere, can only slow the process. They can't stop it. Gradually, the internal temperature gradient flattens. The churning mantle of a rocky world solidifies. The dynamo generating its magnetic field sputters and dies. The subsurface ocean, if it existed, begins to freeze from the bottom up. The high-pressure ice at the ocean floor thickens. It creeps upward until the last liquid pocket is squeezed out. The world becomes geologically dead. The final state is a kind of thermal equilibrium with the universe. The planet's temperature approaches that of the cosmic microwave background, the faint afterglow of the Big Bang. Just a few degrees above absolute zero, it becomes a nearly isothermal sphere, the same bitter cold from its surface to its core. No more internal fires. No more hidden seas, just a uniform, profound freeze. This heat death is the ultimate fate. It turns even the most promising potential haven, with its warm, dark ocean, into a uniformly frozen world. A sculpture in ice and rock, this timeline is the key to their personal history. A rogue planet's current internal temperature is a direct readout of its age and mass. A warmer giant suggests a younger object, perhaps recently ejected. A colder one is an ancient traveler. For a rocky world, even a faint trace of geothermal activity could hint that its internal clock hasn't yet run down. That somewhere beneath the ice, an ocean might still persist. By learning to read this thermal signature, astronomers can do more than find these worlds. They can begin to write their biographies. They can distinguish the youthful exiles from the primordial elders, and understand which dark wanderers might still, against all odds, hold a whisper of warmth within. Even a world without a sun can still have light in its sky. Out in the deep dark between stars, a rogue planet with a strong magnetic field might create its own auroras. These wouldn't be like Earth's, those green curtains from the solar wind hitting our air. The source here is different, more subtle. The particles could come from the thin stuff between stars itself, gathered up and sped along by the planet's magnetic field as it moves through the galaxy. Or if the planet has a moon with active volcanoes, geysers shooting material into space could provide a local source, charged particles. The result would be a ghostly glow. A faint, maybe planet-wide light in strange colors, deep violets or blood reds from excited molecular hydrogen, colors no human eye has ever seen in a sky. A silent, perpetual light show in an eternal night with no one there to see it. This idea, this poetic possibility, shows something important. It shows that active processes can keep going in total isolation. Magnetism, particle acceleration, atmospheric chemistry. The rogue planet isn't just a frozen statue. It can be an engine, quietly making its own ethereal beauty against the black. A beacon, not signaling with radio waves or heat, but with a whisper of colored light against the endless dark. That silent magnetic beacon drifts, but its path isn't really its own. There's a larger force at work, a more patient one. It sculpts the journeys of every object in the galaxy over immense timescales, the galactic tide. Not a tide of water, but of gravity. The entire mass of the Milky Way, billions of stars, the dark matter halo, all pulling together. That collective gravity creates a smooth, pervasive field. And within that field, an object like a rogue planet feels a subtle pull, a differential pull. The side of the planet a bit closer to the galactic center feels a slightly stronger tug than the side farther away. That difference is the tide, an incredibly weak force but constant. Over billions of years, it can gently bend a planet's solitary path, reshape it. For a rogue planet drifting in the galactic disk, this tide acts like a cosmic hand, slowly guiding its motion. The effects are profound in their patience. One possible outcome is a slow lift. The tidal forces can gradually add energy to the planet's orbit, raising it out of the thin galactic disk. Over eons, the path may steepen, carrying the planet up into the vast spherical halo that surrounds the galaxy. It transitions from a traveler among the stars to a solitary voyager in the much emptier space above and below the starry plane. Its journey becomes even more isolated. The sky grows darker as the dense disk recedes below. Conversely, the tide can also have a circularizing effect. If a planet is on a very elongated path, an eccentric one, maybe from a violent ejection, the persistent tug of the galactic tide can smooth that out. It can gradually bleed away some of the extreme motion, rounding the orbit into a more placid, circular path around the galactic center. The planet's wild, swinging journey settles into a stately, endless loop. This is evolution on a scale we can hardly comprehend. The galaxy itself is the choreographer, and the rogue planets are its slowest dancers. Their individual stories, ejection, lonely birth, that's just the first chapter. The second chapter is written by the galaxy, in the language of gravity and deep time. This adds a profound layer of dynamism to their existence. A rogue planet isn't simply flung and forgotten, traveling a fixed line forever. Its voyage is an interaction, a conversation with the entire mass of its home galaxy. That means its ultimate destination isn't random. It's shaped. A planet that might have drifted between the spiral arms for eons could be slowly shepherded back toward the crowded disk by these same tidal forces. Or one born in the halo could be gradually drawn downward. Their distribution across the galaxy isn't static. It's a slow-motion flow, a circulation of dark worlds driven by the gentle, inexorable pull of the whole. This concept ties the fate of the smallest wanderer to the largest structures. It suggests that to truly understand the journey of a single dark planet, you must also understand the gravitational anatomy of the Milky Way. Their long-term orbits become tracers, maps of the galaxy's invisible tidal field. By simulating where these planets should gather after billions of years of such influence, astronomers can test models of the galaxy's own mass and shape. The silent paths of the orphans become, in their own way, a tool for cosmic cartography. They are not just passengers in the galaxy. Over deep time, they become its subtle, responding instruments. A ring system around a rogue giant would be a sculpture of stillness. Saturn's rings are shaped by the Sun's gravity and radiation, which creates gaps and waves. But a rogue planet's rings are in a near-perfect vacuum of influence. There's no solar wind to erode the icy particles, no shepherd moons, likely lost when the planet was ejected, to carve sharp edges through gravitational nudges. The rings are left to their own devices, governed only by the planet's gravity and their own slow, mutual interactions that could allow for structures of astonishing stability. Rings that have persisted, essentially unchanged, since the planet's formation billions of years ago. They'd be primordial archives, their particle size, distribution, and composition frozen in time, telling the story of the circumplanetary disk that birthed them. A silent, circular record of the planet's own infancy. Seeing these dark hula hoops would be a profound challenge. They emit no light of their own. Their visibility would depend on rare and fleeting circumstances. If the rogue planet, by pure chance, passed directly in front of a distant, bright star, the rings could reveal themselves, not by reflecting starlight but by blocking it. As the planet transited, astronomers would see a complex, symmetrical dimming pattern, a central dip from the planet itself, flanked by smaller, precise dips from the rings. It would be a shadow play on a galactic scale, lasting perhaps only hours, or the rings might betray their presence through a faint thermal signature. The icy particles, though bitterly cold, would still radiate a minuscule amount of heat in the far infrared. Against the even colder backdrop of space, a sensitive telescope like the James Webb might detect an anomalous, extended glow around the planet, a diffuse halo of warmth that hints at the vast, frigid disk. The aesthetic is one of profound serenity, ice and dust particles ranging from tiny grains to boulder-sized chunks in a slow, stately orbit. They trace perfect circles or gentle ellipses in the blackness, their dance undisturbed for eons. There are no storms here, no dramatic light shows, just the relentless, graceful pull of gravity. It's a frozen ballet performed for an audience of none. The rings become an extension of the planet's solitude, a beautiful, intricate, and utterly silent monument to isolation. A crown of ice and shadow, worn by a king that rules over nothing but the endless dark. That silent arc drifting out there in the dark, it holds a deep possibility. It connects to one of the big ideas in science, interstellar panspermia. The idea that life, or the pieces for it, could travel between stars, that Earth might not be the only cradle. It could be a stop, a waypoint in a much larger story. And a rogue planet with its ocean under the ice is the perfect ship for that. Think of crossing between stars. The radiation out there is intense, cosmic rays, stellar flares. It can break apart complex molecules, sterilize anything exposed. A ship would need heavy shielding, but a rogue planet has that, naturally. Its crust of ice, kilometers thick. That's a perfect radiation barrier, and inside, in that ocean, any microbes or chemistry is cradled there. A dark, pressurized, stable environment, insulated from the voyage outside. Now give that arc a journey. It drifts for 1,000,000 years, 10 million, 100 million. Time in the cold of space isn't really an enemy. It's more like a medium. For a dormant spore or a microbe adapted to a sunless sea, these spans aren't impossible. It's a long sleep. The planet's own warmth keeps the water liquid. The chemistry continues, and all that time this biological cargo is moving across the vast distances. Then the final step, delivery. The rogue planet's path brings it by chance into a new solar system. A young one, maybe it gets captured into an orbit, or maybe it has a glancing collision with a rocky planet there. The impact would be catastrophic locally. But it could also be generative. Material from the rogue planet's ocean, frozen or liquid, could splash onto this new world. If that world has the right conditions, water and atmosphere, those hardy travelers have a new home. A fresh start under an alien sun. This is all speculative, of course. It rests on a chain of unlikely events. Life starting in a sunless ocean, surviving an ejection, enduring an eon-long voyage, then colonizing a new world upon arrival. The odds for each step are long, but in a galaxy with billions of these arcs, each traveling for billions of years, the improbable might become inevitable. Somewhere, the idea changes the rogue planet from a curiosity or a fossil into a potential gardener, a silent sower of biological potential across the galaxy. It puts these dark wanderers at the center of a big question. Is life on Earth unique, a local phenomenon, or could it be a galactic traveler, a story written not just on one world but carried between them? The rogue planet offers a mechanism, a slow, patient, incredibly robust ship for that transit. It suggests that if life can begin in the warm, dark heart of a frozen wanderer, then the seeds of biology might be scattered far more widely than we thought. Our own origin might not be confined to the light of our sun. It could be woven into the endless, starless journeys of the dark ships sailing between them. But that silence might not be complete. There's another way to listen for them, a method that doesn't rely on light or heat at all. It listens to space itself. The collision of two massive rogue planets would be quiet. No flash, no radiation burst, just two dark spheres of rock and ice or maybe gas merging in the dark. But an event like that would send a tremor through the cosmos, a ripple in space-time, a gravitational wave. Our current observatories, like LIGO, are built to hear the universe's most violent events. The mergers of black holes and neutron stars, events that shake space-time at high frequencies. The signal from two planetary objects colliding would be different. It would be a low, deep thud, a bass note far below what our ground instruments can detect. Those waves would have wavelengths measured in hours or days, not fractions of a second. To hear that deep thud, you'd need a new kind of ear out in the quiet of space. Future missions like the proposed LISA are designed for this. 3 spacecraft flying in a vast triangle millions of kilometers apart, connected by lasers. They'd measure the tiny stretching and squeezing of space between them. That system would be sensitive to the low-frequency hum of massive objects moving together. So imagine the scenario: 2 rogue ice giants, each several times Earth's mass, drifting alone for billions of years. Their paths, shaped by the galactic tide, finally intersect. They spiral together, pulled into a final, silent embrace. As they merge, they churn the space around them. That disturbance moves outward at light speed. A spherical wave of distorted space. Years, centuries, millennia later, that wave passes through our solar system. It stretches the distance between the LISA satellites by less than the width of an atom. The lasers see the shift, a quiet spike in the data, the signature of a dark collision long ago and far away. This would be a detection of pure gravity. We wouldn't need to see the planets or sense their heat or hear any magnetic song. We would feel their impact, a direct census of the unseen. Each signal would tell us not just that 2 objects merged, but roughly how massive they were and how far. By listening for these deep space thuds over time, we could start to map the rate of these dark mergers. Are they common? Do they happen mostly in the crowded disk of the galaxy or out in the halo? The gravitational echo becomes a new kind of evidence. It reveals the hidden dynamics of a population we can't see, through the vibrations they leave in the stage they move on. It turns the quietest, darkest event imaginable into a source of signal, a whisper from the void written not in light but in the bending of the universe itself. These dark wanderers, they've always been more than just astronomical curiosities. They're mirrors for our own ideas about solitude, about survival, about the hidden corners of existence. In that absolute isolation, they become a canvas for our stories. Science fiction has always been drawn to this image, the sentient planet Solaris, a vast thinking ocean adrift in space. Or frozen, derelict worlds as backdrops for exploration and horror. These narratives use the rogue planet as the ultimate frontier, a place so removed from the familiar rhythms of suns and seasons. It forces characters to confront fundamental questions, and by extension, us. What does it mean to be a world? Can consciousness arise in total darkness? These stories turn the rogue planet from a setting into a character, one defined by its silence and its secrets. That cultural resonance taps into something universal. Resilience in the face of abandonment. The rogue planet is the ultimate castaway, thrown into the void yet enduring. Its very existence against all odds becomes a metaphor for hidden potential, for an inner warmth that persists when all external light is gone. It suggests vitality isn't always where we expect to find it, that it can flourish in the most isolated, sunless places, and that idea challenges a very human perspective. For millennia, our myths have linked life and purpose to light, to solar cycles, to growth under a sun. The rogue planet quietly dismantles that. It proposes a universe where complexity, maybe even consciousness, doesn't require a star's blessing. It can be born from internal fires, from gravitational embraces, from chemical patience in a dark sea. Philosophically, that's a humbling shift. It moves us away from an anthropocentric view, even a soul-centric view of the cosmos. If a planet drifting in eternal night can harbor a subsurface ocean, and that ocean might foster life, then the conditions for existence are far more varied than we imagined. Life isn't a rare accident of a star's Goldilocks zone. It might be a latent potential within the cold, dark chemistry of the galaxy itself, waiting for any stable, warm pocket to awaken. The rogue planet becomes a symbol of that decentralized possibility. Its journey suggests purpose isn't bestowed from above by a central sun. It can be generated from within, through its own dynamics and history, and that reframes our place in the narrative. We aren't the privileged inhabitants of a uniquely blessed star system. We're perhaps one expression of a cosmic tendency, a tendency that might be quietly at work in countless dark, drifting vessels. The artistic and scientific fascination with these worlds, it's the same impulse at its heart. A search for meaning in the darkness, a desire to understand whether the loneliness we project onto them is truly empty, or if it contains a different kind of fullness. A warmth that doesn't come from a sun, but from the slow, patient heart of a world itself. The search for these silent wanderers is about to leap forward. For decades, they've been statistical phantoms, fleeting anomalies in starlight, but a new generation of observatories is being built, designed not just to glimpse their shadows, but to see the worlds themselves. The hunt is accelerating from detection to characterization, and it promises to fill the dark with names and details. Leading this charge is the Nancy Grace Roman Space Telescope. Scheduled to launch before the end of this decade, its primary mission includes a monumental microlensing survey. Past efforts monitored millions of stars. Roman will stare at hundreds of millions continuously, with a wide field view unmatched by any previous space telescope. Its sensitivity is the key. It will catch the subtle brightening caused by planets far smaller than Jupiter, down to the mass of Mars, even free-floating Earths. The numbers are staggering. Instead of a few dozen candidate events, Roman is expected to find thousands of rogue planets. It will deliver the first robust demographic survey of this hidden population. We will finally have reliable statistics. How many are there per star? What is the distribution of their masses? Are they more common in the galactic bulge or the spiral arms? Roman's data will transform rogue planets from theoretical predictions into a quantified, mapped reality. It will tell us if they truly are the galaxy's silent majority. But microlensing, for all its power, is still an indirect method. It gives us mass and distance, but little else. To truly know these worlds, their composition, their atmospheres, their temperature, we need to see their own faint light. That requires a different kind of eye, one tuned to the deepest cold. Future concepts for direct imaging focus on the mid to far infrared, where a cold rogue planet's own heat signature is brightest. Imagine a telescope not just cooled but cryogenic, operating at temperatures near absolute zero to eliminate its own infrared glow. Such an instrument, placed in the deep quiet of space, could directly detect the thermal emission of a rogue gas giant relatively nearby. It would appear not as a distorted flash, but as a steady, faint pixel of warmth against the cosmic backdrop. Even more ambitious are ideas for large space-based interferometers. Instead of a single mirror, these would use multiple telescopes flying in precise formation, combining their light. This technique, called interferometry, creates a virtual telescope with a resolution equivalent to the distance between the collectors. It could, in theory, resolve the disk of a nearby rogue giant, not just a point of light but a blurry sphere. We could see if it has bands or spots, measure its rotation, perhaps even detect asymmetries hinting at weather patterns in its frozen atmosphere. These missions are on the drawing boards of space agencies. The next logical step after the James Webb and Roman telescopes, the promise is profound. Within a generation, the catalogue of known rogue planets could swell from a handful to many thousands. A small percentage of those, the nearest and largest, will become subjects for intense study. We will move from asking if they exist to asking what they are. What gases linger in their atmospheres? Do they show signs of complex hydrocarbon chemistry? Does their thermal profile suggest a layered, settling structure or dynamic internal heat? Each answer will be a clue to their origin, ejected giant or dark-born solitary. This isn't just about adding entries to a list, it's about populating the void. Giving context to the darkness, the statistical ghosts that have haunted our models for so long are about to become a gallery of worlds, each with its own story, waiting in the data stream to be told. The eternal night is finally being fitted with eyes. That gallery of worlds starts with numbers, a mountain of them, data. Every night, telescopes in Chile, South Africa, Australia, the Korea Microlensing Telescope Network, KMT-net, they scan the star fields toward the galaxy's center. They're not taking pictures, they're logging brightness for hundreds of millions of stars, night after night for years. Each star's measurement is a single point in a river of data. The goal is to catch an anomaly, a star that brightens for a few hours or days, then fades. That curve of light hidden in the noise is the only clue. It's the entire case file for a dark planet, but finding it is like listening for one whisper in a roaring stadium. The data stream is overwhelming. It's measured in petabytes. Millions of gigabytes, a volume no human team could sift through. So the story shifts from telescopes to algorithms. It becomes a digital detective story. Astronomers and data scientists train machine learning models. They feed them millions of simulated light curves. They show them what a perfect microlensing event looks like, from a Jupiter-sized rogue, from an Earth-sized one. And they teach them all the other reasons starlight can flicker: a variable star's pulse, atmospheric jitter, an instrumental glitch. The algorithm learns the signal's signature in an ocean of false alarms. It combs the petabyte mountain, flagging candidates, the ones with that symmetric brightening curve. But an algorithm's flag is just the start. Human intuition takes over. Astronomers from OGLE, they examine these candidates, a forensic analysis, they check and recheck. Could this be a binary star system, a star with a known planet in a normal orbit? They model the light curve with precision, tweaking parameters, the lensing object's mass, its distance, its motion. It's a mathematical puzzle with one correct solution. The whole process, from the first photon to the final announcement, can take years. It's a global effort of quiet persistence, a collaboration across continents on coffee and code, deciphering stories in faint starlight. Each confirmed detection is a triumph of that partnership between human curiosity and machine intelligence. It's a testament to the idea that to find the darkest things, we must first learn to see in the language of data. And in that data, every successful curve is more than a statistic. It's a single, verified chapter, a story of cosmic exile, waiting for its context to be revealed by the next chapter of the search. A world without a sun has no summer, no winter, but that doesn't mean it's without rhythm. The galaxy itself can impose one, a deep, patient pulse measured in millennia, not months. Think of a rogue planet on an elongated path around the galactic center. Its orbit isn't a circle, it's an ellipse, a stretched loop. For most of that immense journey, it's sailing through the space between the spiral arms. The interstellar medium there is thin, a diffuse haze. The planet's magnetic field, if it has one, pushes against this faint resistance. Its upper atmosphere is quiet. But then its path curves inward. It plunges through one of the galaxy's spiral arms. These are the star-forming regions, the nurseries, and they are denser. More gas, more dust, more energetic particles from young, violent stars. This passage is a transition. For the planet, it's like sailing from a calm sea into a region of steady swells. The external pressure increases. The flux of cosmic particles hitting its magnetic bubble rises. This interaction creates a kind of galactic weather. A season. As the planet enters the denser region, its magnetosphere compresses. The boundary where its field holds back the interstellar wind gets pushed closer to the surface. More particles get funneled down toward the poles that could spark brighter auroras, a silent, millennia-long light show, triggered by geography on a galactic scale. The increased particle flux could also heat the very top layers of its atmosphere, causing a faint expansion. Then, as the planet completes its passage and emerges back into the galactic hinterlands, the pressure eases. The magnetosphere expands outward again, the auroral activity dims, the atmosphere contracts back into a deeper freeze. This cycle is achingly slow. A single seasonal transition could last 100,000 years. The planet's entire year, one full galactic orbit, might take 200 million or more. For any process on that world, this is a fundamental metronome. A subsurface ocean's chemistry, stirred by geothermal vents, might experience periods where the overlying ice shell is under slightly different stress. A gas giant's atmospheric distillation might see a temporary shift, as the upper layers are minutely warmed during the dense arm passage. It's a season dictated not by axial tilt, but by orbital geometry. Not by a star's light, but by the galaxy's texture. This introduces a profound form of timekeeping. The planet carries an internal clock from its radioactive heart, ticking down its heat, and it's embedded within an external clock, the rhythm of its galactic journey. Its existence is measured between these two beats. One counting down to eventual cold, the other marking its periodic passage through the bustling and barren quarters of its true home. This cyclical change redefines the nature of a solitary world. It's not adrift in a uniform void, it's a traveler on a road with changing scenery, a road made of star stuff and silence, where the seasons last for eons. And the only summer is a slow immersion into the luminous fog of a spiral arm. Your boots are on a crust of frozen air, that crunch under your feet, that's nitrogen snow. And the sound doesn't echo, there's no air to carry it. You look up and the sky isn't black, it's a river of powdered diamond dust. The whole Milky Way is right there, arcing overhead. A brilliance you can't get on any world with an atmosphere. No sunrise to wash it out, no moon to compete. It's a permanent fresco, silent, lighting these frozen plains in a soft, starry twilight. A twilight that never deepens, never fades. That's the sky of a rogue world, a sky without a sun. The only warmth is faint, almost imperceptible. It comes up through the soles of your boots. It's radiation, the planet's last memory, the final whispers of heat from a core that's been cooling for billions of years. It's not the warmth of a hearth. It's a geological ember, a testament to an ancient, violent birth, almost completely forgotten now. You're standing on the dying breath of a world's internal fire. The silence is absolute. It's not the quiet of a forest. It's the total absence of a medium. No wind, the atmosphere collapsed eons ago. No rustle, no distant water. No hum of insects. The only sound is the one you bring, your own breath, your own heartbeat. And against that backdrop of nothing, it feels deafeningly loud. That's the sound of isolation made physical. You're a visitor here, and this object is, in its essence, a monument, a being of pure gravity and memory. Its gravity is what defines it, holds its frozen form together, keeps it on its endless path. Its memory is locked in the rocks, in the isotopic ratios, in the layered ices of its former atmosphere, the pristine craters on its surface. It remembers the chaos of its formation, the trauma of its ejection, the long, quiet eon of its drift. It doesn't communicate this memory in words or light. It communicates by being, by persisting. From here, the scale of the journey becomes a felt thing. Not just an idea. The galaxy above isn't a distant map. It's the only neighborhood this world has ever known. It sailed beneath those same spiral arms for longer than life has existed on Earth. Gently pulled by the galactic tide, its path sculpted by the collective mass of everything you see above, it is utterly alone, and yet intimately connected to the grandest structure it knows. To stand here is to understand a different kind of time. Human history feels like a fleeting spark, even planetary history. This world operates on a different clock. Measured in the radioactive decay of its core, the slow precession of its galactic orbit, its seasons last for millennia, defined only by its passage through slightly denser or thinner regions of interstellar space. Its destiny is to cool evenly and completely until its temperature matches the faint afterglow of the Big Bang itself. It's headed for a perfect, uniform cold. And yet, in that profound loneliness, there's a staggering resilience. This world was cast out. It lost its sun, its place in a family of planets. It endured a transition that would shatter most stories. And yet it persisted. It didn't fly apart. It didn't vanish. It settled into a new, solitary identity. It became a keeper of its own history, a traveler on a road so vast we can barely conceive of it. It found a rhythm in the galactic tide, a purpose in its own slow transformation. In that, maybe, lies the deepest lesson these dark wanderers offer. They reframe resilience. It isn't always about thriving in the light. Sometimes it's about preserving a whisper of warmth in an eternal freeze. It's about holding your shape against the void. Carrying a record forward, even if there's no one to read it. They are the galaxy's archivists, its silent sentinels. They remind us that existence takes many forms, and that a journey through perpetual night can be, in its own stark way, a story of profound and enduring grandeur. They started with violence. They endure in silence. These rogue planets, they come from the chaotic nurseries of young stars. They drift through the vast, empty passages between the spiral arms. They're not just oddities, they're fundamental pieces of the galaxy. They're hidden architects of its gravitational landscape, and they're potential crucibles. They hold the quiet possibility for life in the most unexpected places, sunless places. Their existence is a reminder. The universe operates on principles of immense diversity and profound resilience. Life, its potential, it isn't confined to the warm, lit gardens around stars. It might stir in the deep, pressurized dark, sustained by inner warmth. By ancient chemistry, our tools are evolving. The Roman Space Telescope will conduct a statistical hunt. Future observatories will hear their gravitational whispers, see their faint infrared glow. These dark wanderers will step from the shadows of theory into the light of our understanding. They'll transform from ghosts in the data into a catalogue of worlds, each with a biography written in ice, in rock, in motion. The eternal night is not empty. It is richly populated. Its silent citizens have much to teach us about the galaxy's past, its structure, the tenacity of existence itself.